Welcome back, class. So in this problem, we're again dealing with another weak acid equilibrium problem, but in this one, we're given the concentration of a weak acid and we're told the pH, and we're asked to find the Ka. So unlike the first example problem we did, where we were asked to find the pH, here we're given the pH and asked to find the Ka of some unknown weak acid. Well, we can again use similar ideas to figure this out. So the key connection here is when they tell you the pH, what they're giving you is enough information to find the equilibrium hydronium concentration. So we can do that, of course, by using our pH equation, right? So we know the pH is equal to the negative log of the hydronium ion. Now, of course, we want to find the hydronium. So if we want to find what's in here, the appropriate equation is going to be the hydronium ion concentration is equal to 10 to the negative pH. So if we plug this in, we get 10 to the negative 3.25. And so if we do that, that tells me that the hydronium ion concentration equals 5.62 times 10 to the negative 4. Okay, so now we have our hydronium ion concentration. We can go ahead now and start working our equilibrium problem. Now, one thing that we need to, again, sort of get an understanding of is we don't even need to know what the acid is to do an equilibrium problem because they all follow the same equilibrium. Right? Our generic weak acid equilibrium is going to be that our acid plus water is in equilibrium with our conjugate base. So it's going to be the acid anion, right? Plus hydronium ion. Now, of course, all of these are aqueous except for the water, who's always in the liquid form. Now, the generic Ka expression, right, for a weak acid equilibrium is going to be the Ka equals the conjugate base times hydronium concentration over the concentration of our acid. So if we go ahead and make up our Rice table, where we have Ha, A minus, and hydronium, and so what do we know? What we know now from this problem is we know the equilibrium concentration of hydronium ion right here. So that's going to go right down here. So 5.62 times 10 to the negative 4. Now, what else can we fill in here? Well, we know the initial concentration of our acid, right? It's a 0.175 molar. And we know that these are going to be 0 to start at the very beginning, right? Before we imaginary see any dissociation. So at the beginning of the process, we're going to start with acid and essentially 0 of our hydronium and our conjugate base. Now, as we approach equilibrium, these are going to change, right? And based on our stoichiometry, this is going to go up by x. But let's think about it. We don't even need to do the x variables here because we already have an equilibrium concentration. So we can do a problem like our sort of second step in when we did equilibrium problems, right, where we can just work for the change. So that means our change here is a positive, is a positive 5.62 times 10 to the negative fourth. And based on our stoichiometry, each of these reactants are going to go down by the same amount. So we can fill that into our Rice table. And now we can go ahead and do our math. And so our equilibrium concentration of our acid is going to be 0.175 minus our change, which is going to give me 0.174, right? Notice very little change. And our conjugate base is going to be 0 plus the 5.62 times 10 to the negative fourth, or simply 5.62 times 10 to the negative fourth. So now we very readily have our equilibrium concentrations, and so now all we have to do is plug them into our equilibrium expression to solve for our Ka value. So as we write these in here, .174 for the acid. We do the math, and we'll get a Ka value 1.82 times 10 to the negative sixth. Right, so it's another sort of type of weak acid equilibrium problem, but this time instead of being asked to find the pH, we're given the pH and asked to find the Ka. All right, so we're going to continue to do some problems here, and the next one we're going to look at is this idea of percent ionization, and we'll see that this is, again, closely related to this whole equilibrium problem.